Hello everybody, I am Anandavalli from Guidance Education channel. Welcome to this new video from the channel. We are continuing class 11 chemistry, classification and periodicity of properties. Periodic properties, part 13. Under this we will be discussing electronegativity. The subtopics are definition, comparison with electron gain enthalpy, electronegativity scale, factors affecting electronegativity, trend of electronegativity, applications of electronegativity. Watch the video completely in order to get all points clear. And if you think the video is useful, do like the video, share the video with your friends and also leave your valuable feedbacks as comments in the comment box below. This helps me to understand your thinking about the video and the content. If you are watching without subscribing my channel, do subscribe it now and support me. Subscriptions as usual are free. Do not forget to recommend my channel to your friends in other groups. Press the bell button and all button for notification of more videos like this. Thank you very much. Come, let us start the class. Electronegativity. Symbol Chi. Definition. Electronegativity of an element is the tendency of the element to attract the shared pair of electrons towards itself in a covalent bond. So it is all about covalently bonded atom. Features. It is not measurable. It cannot be measured experimentally. It is only a relative number. It is a property of the bonded atom, not isolated atom. It is not a constant number for any atom. It depends on certain factors. Changes regularly in a period, though there are exceptions. Electronegativity is different from electron gain enthalpy and ionization enthalpy. We will just see a comparison between electronegativity and electron gain enthalpy. Corresponding features of electron gain enthalpy. Electron gain enthalpy can be measured experimentally. Electronegativity cannot be measured. While electronegativity is a relative number, electron gain enthalpy is measured in the unit of kilojoules per mole. Electron gain enthalpy is the property of isolated atoms. Electronegativity is the property of bonded atoms. Electron gain enthalpy is constant for an atom, whereas electronegativity is not constant for any atom. Electron gain enthalpy as well as electronegativity depend on certain factors. That is one similarity. Another similarity is that both are periodic properties. If you are asked to compare these two quantities, that is electronegativity and electron gain enthalpy, you have to list the differences as well as the similarities. That is why I specially mentioned the similarities. There is no regularity in the change of electron gain enthalpy in a period or group, whereas for electronegativity, there is regularity. Of course, with some exceptions. Let us proceed further. We said electronegativity is not measurable experimentally and it is a relative number. What is meant by relative number? For that, we have to understand electronegativity scale. Though a number of scientists have proposed electronegativity scale in their own method, we will mention three important among them. Pauling scale, second one, Jeffy scale, Alfred Rochow scale. A detailed discussion of these scales is beyond the scope of this syllabus, yet I will make a mention of a few details of Pauling scale. According to Linus Pauling, chi A minus chi B is equal to 0.1017 into root delta. Chi A is the electronegativity of element A and chi B is the electronegativity of B. A is bonded to B. Delta is equal to bond dissociation enthalpy of AB raised to minus root of bond dissociation enthalpy of AA multiplied by bond dissociation enthalpy of BB. I will explain bond dissociation enthalpy. Bond dissociation enthalpy AB is the energy needed for breaking the bond between A and B. Similarly, the energy needed for breaking the bond between AA and the energy needed to break the bond between BB. Linus Pauling calculated the electronegativity of different elements using this formula. Fluorine was arbitrarily allotted a number equal to 4 and it was the greatest value. The value of electronegativity for other elements were ascertained in relation to the electronegativity of fluorine. That is why the electronegativity is known as a relative number. Almost all books give the electronegativities of the representative elements as per Pauling scale. I have not included that in this video. So now you know why it is a relative number. It is only a number. It has no unit. Fluorine is supposed to be the most electronegative element and cesium, the last element in the first group, is supposed to be the least electronegative. That is, fluorine has a maximum capacity to attract electron towards itself and cesium the least. The relative electronegativity of cesium is 0.7. Now we will proceed to discuss factors affecting electronegativity. We have already said the electronegativity of any element is not constant and that it depends on certain factors. First one, state of hybridization of the atom. Second one, oxidation state of the element in the compound. And the third one, nature of the substituent attached to that element. You will learn hybridization in the next chapter, that is chemical bonding and molecular structure. Here I will clarify the term in simple words. Hybridization is a term used to explain chemical bonding in certain compounds. That is, to explain how the molecule of that compound is formed. As per the concept of hybridization, the atomic orbitals of slightly different energy levels of the same atom get mixed up to produce molecular orbitals at the time of formation of molecules of compounds, and the orbitals which are formed newly will have the same shape and energy. The different orbitals are s, p, d and f. At present we are concerned only about s and p. We know s has one orientation and p has three orientations, d has five orientations and so on. If s orbital mixes with one of the p orbitals, then that hybridization is called sp hybridization. That will give rise to two molecular orbitals. If the s orbital mixes with two of the p orbitals, it is sp2 hybridization. That will give rise to three molecular orbitals of the same energy level and shape. If the s orbital mixes with all the three p orbitals, then it is sp3 hybridization, and that gives rise to four molecular orbitals of the same shape and energy. When we come to the electronegativity of these three different types of hybridized carbon atoms, it is seen that the sp hybridized atom has more electronegativity than sp2 than sp3. So the electronegativity of that atom depends upon the compound in which it is present. So for any element, it is not constant. Now the second factor, oxidation state. Elements belonging to the D block, that is transition elements, have different valencies. They have variable valencies. They acquire different oxidation states in different compounds. You have already learned that the same transition metal, when it acquires different oxidation states in different compounds, they take up different colors. Let us take the example of iron 3 plus and iron 2 plus. 2 plus. Iron can form compounds. Electronegativity of iron in compounds where iron is present as iron 3 plus will be more than the electronegativity of iron present as iron 2 plus in another compound. So the same element acquires different electronegativity because of the difference in the oxidation state. So the electronegativity of iron 3 plus is greater than that of iron 2 plus. So we may say as the oxidation state of an element in the compound increases, the electronegativity also increases. The third factor is nature of the substituent attached to the atom. We will consider two compounds having carbon. First one, iodomethane and trifluoroiodomethane. In iodomethane, the carbon atom is attached to 3 hydrogen atoms and 1 iodine atom. In trifluoroiodomethane, the carbon atom is attached to 3 fluorine atoms and 1 iodine atom. The carbon atom in these two compounds have different electronegativities due to the difference in the substituents. When iodomethane dissociates, iodine acquires a negative charge, and when trifluoroiodomethane dissociates, iodine acquires a positive charge. Therefore, it is understood that carbon atom in trifluoroiodomethane is more electronegative than the carbon atom in iodomethane. In iodomethane, the iodine atom is more electronegative than the hydrogen atom present. That is why iodine acquires a negative charge when iodomethane undergoes dissociation. So iodine has more power to attract electrons than hydrogen in iodomethane. Therefore, the carbon atom in iodomethane is less electronegative. In trifluoroiodomethane, the fluorine atom is more electronegative than iodine. That is why when it undergoes dissociation, the iodine atom acquires a positive charge. So the carbon atom in trifluoroiodomethane is more electronegative. So accordingly, the carbocation is formed from iodomethane, whereas carbanion is formed from trifluoroiodomethane. So carbon atom in trifluoroiodomethane is more electronegative than the carbon atom in iodomethane. If you have any doubts, please comment in the comment box. Trend of electronegativity. Electronegativity increases from left to right of the periodic table, that is across the period, and decreases down the group. The reason is atomic number increases and atomic radius decreases from left to right, and atomic number and atomic size increases down the group. Screening effect also increases down the group. We have already discussed screening effect in one of the previous videos. What are the applications of electronegativity? First one, predicting the metallic or non-metallic property or characteristic of elements. Second one, understanding the polarity of bond. This is with reference to covalent bonds. Based on the difference in the electronegativity of the participating atoms in a compound, one end of the molecule acquires a delta positive charge and the other end acquires a delta, that is partial negative charge. This is what we mean by polarity. Before we discuss that, let us see how metallic and non-metallic character is predicted. As electronegativity chi increases, the non-metallic property also increases. We have already seen that in the whole periodic table, fluorine has the greatest electronegative value equal to 4. So, fluorine has greatest non-metallic property. Similarly, when chi decreases, metallic character increases. So cesium, which has the least electronegativity, has greatest metallic property. In general, the left hand side of the periodic table, which has metals, they have the least electronegativity. And on the right hand side of the periodic table, where you find non-metals, those elements have the greatest electronegativity. The electronegativity increases from left to right. We have already seen the trend. Down the group, especially for transition elements, the electronegativity decreases. We have already seen the reasons for that. So, metallic property increases. Coming to the second application, when two atoms are linked by covalent bond and if the two atoms are similar, as in the case of hydrogen molecule, the shared pair of electrons will be exactly in the central point between the nuclei of the two participating atoms. This is because their electronegativities are the same. Such molecules are called non-polar because the electrons of the pair is equally shared by the two atoms. But the covalent bond in hydrogen chloride is not like this. The shared pair of electrons will remain closer to chlorine atom because chlorine is more electronegative than hydrogen. So chlorine develops a delta negative charge, that is a partial negative charge, and hydrogen develops a partial, that is delta positive charge. So the molecule is a polar molecule. So in the molecule, one end of the molecule develops a negative charge and the other end develops a positive charge. There is charge separation. Such molecules are polar molecules and they have partial ionic property or character. The charge separation or polarity of the molecule is measured in terms of dipole moment. Greater the difference in the polarity of the participating atoms, greater the dipole moment. For example, the difference in the electronegativity of chlorine and hydrogen in hydrogen chloride molecule will decide the polarity of hydrogen chloride. That is dipole moment. The polarity of hydrogen halides decrease from hydrogen fluoride to hydrogen iodide. If the electronegativity difference between the bonded atoms is less than 1.9, it is predominantly considered as covalent. And if it is greater than 1.9, it is predominantly ionic. So, ionic compounds have greater dipole moment than covalent compounds. Hope this video was of great use to you. If you think it is useful, do like the video, share the video with your friends and also leave your feedbacks as comments in the comment box below. If you're watching without subscribing my channel, do subscribe it now and support me. Press the bell button and all button for notification of more videos like this. Thank you very much. We will meet in the next video with another important topic. Till then, bye. Take care.